So first, I want to talk about processes, what processes are on a computer. Does anybody here have a good idea of what a process is already?
I mean, it's execution on the computer that has its own memory space, and I guess depending on the architecture, you can have threads within that process.
Yes.
That's about my extent of my knowledge, to be honest.
That's good. That's good. So I'm not going to go too deep into it, but if you open up a terminal and you type welcome whoever came, I can't see, but somebody just joined us. Ethan, welcome, Ethan.
Howdy.
We just started, and this was my first real slide, was let's talk about processes. So
Okay, thanks for catching me up.
If you open up a terminal and you type Node, assuming that you have Node installed, then a Node process opens and it sits there and it just waits for you to type at it. And then when you type and hit enter, then it does stuff. If you look at the Node process, so, and this one I'm just running Node and I type in some stuff, but if I ls, meaning list, and -lah is just show details basically. And then which node will give the full path of nodes so that ls has something to interpret. For those of you that aren't super bash savvy, that's what that's doing. But the meat of what we're interested in is this right here. So the node binary is 40.9 megabytes. So there's different optimizations that computers do while a process is running and such, but basically you can assume that because the node binary is 40.9 megabytes, that 40.9 megabytes of data have to be loaded into memory in order for that node program to run. Now, because computers have swap and paging and ways of managing memory and compressing memory, it can actually take up less because things that aren't used could be paged out. But this is important to know that when you run a process, whatever the size of the file is that you're trying to run, like Node or Ruby or Python or whatever it is, along with libraries that it includes. So in the case of Node, that would be OpenSSL is a C library that is used for encryption. libuv is also a C library that is used to make stuff like HTTP and DNS work well across Windows, Mac, and Linux. That is loaded in there as well. So you can expect that when Node loads, it's going to be a little bit more than 40.9 megabytes. Now, there are a couple of different processes you can use to see what programs you can use to see what processes are. One of them is htop. And if you open up one of these programs, when you have Node running in a terminal, like in the case here, there's this highlighted line towards the bottom, it's highlighted in blue, and it gives the full path here to the Node binary that's being executed, which you can't see it all the way, but you can kind of see what folder it's in there. The users AJ local op node v12 da 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 da. So it gets a name that you can see. And if you're on Windows and you do, like, it used to be Control-Alt-Delete. I don't know if that's still what it is, but it would open up Task Manager and it'd show you something similar. And in fact, on Mac, I could have opened up Activity Monitor and we could have also seen Node. But a process is a program that runs, and you can see using various either command line or desktop tools what those processes are, how much memory they're taking up. And we can see here the Node process is taking up 46 megs of, oh wait, hold on, what are we looking at? Oh, no, that's not residential. Residential is 2 megs, it looks like. I don't know, I'm not actually sure how to read this, but it's taking up some amount of memory. It has pre-allocated 4 gigs of virtual memory, which is probably for the V8 virtual machine. And we could see how much CPU it's using, process time, stuff. So you can look at this, like I said, using on Mac, you can use Activity Monitor. On Windows, you can use Task Manager. And then the command line, you can also use tools like PS, top, HTOP, and these show you processes. Oh, that's weird. I duplicated that by accident. And then this was a superfluous example of more things that you can see in HTOP. And okay, so when we run a program, it can have, a program can actually spawn multiple processes. It can spawn multiple threads. And we're going to talk a little bit about what those mean. So first, let's consider the worst case scenario, which is we're running a single process and a single thread, which means that it is a single task has to run all the way through to completion before another task can complete. So I'll post this link in the chat, but I want you to actually go here so that we can experience this in action. Let me see if I can find where the chat window went. I actually am not clear on where the chat window went. Can somebody post this in the chat window? Because I, as the presenter, I think because I'm screen sharing, I don't have the chat window. But coolage86.duckdns.org, port, whoops, I clicked through, port 8001. And what I want to have happen, oh, here's the chat. Let me pull this over to the other window. Oh, great, thank you. Okay, so go ahead and go there. And whoops, it's gonna load for everyone. I'm gonna bring it out on this other screen. I think somebody clicked download already. Is that true? Did somebody click download? Because it's not loading for me right now. And I'm suspecting that's because someone is on the page. If you are on that page and there is not an X in your, or it doesn't have this icon, it has an X instead, click the X if it's not loaded. Okay, so what I just experienced, at least, I don't know if it took like 10 seconds to load for y'all, but it took a while to load for me because somebody else was doing something. So if I click on download on this file, somebody else now click on download, click to download. This is a very big file, so it's going to take 5 minutes to finish downloading. And what you should experience is that nothing happens, because when there's a single process and a single thread, like this very dumb web server that is a Python web server, nothing can happen for anyone else while something's happening for me. So if I click cancel, then someone else's download is going to start. And then if you're doing that, then you'll have to click cancel for it to start for someone else. So when you have a single process and that single process is only running its main thread, it can only do one thing at a time, and that thing has to carry out all the way to completion until something else can finish. So any questions about this so far? All right, cool. Likewise, oops. If we, and I'll just bring this one up actually. So, oh, I can't bring it up there. I'll have to go to the other server to bring it up because somebody else is doing something. So that's from the server perspective. If we look at a browser perspective, a way to see what a single process, single thread looks like is if I click the tickle button here, it pops up with a synchronous blocking modal that is running in the main thread. So now if I click poke or click or tickle again, nothing can happen. So I'm tapping away. I should have put text on the screen so you could see that I can't highlight text. Like the entire browser tab is completely blocked. And if I click OK, then then I can highlight things again.
I can't resist the temptation to point out that Mozilla the MDN has some slight exceptions to that, where there are a few things a tab can actually do when the thread is otherwise blocked. The tab is otherwise blocked.
Do tell.
Yeah, I don't remember exactly what it is. I'll have to pull it up. But there are some real edge cases to this. One of them that I ran into 7 years ago when I was doing hybrid mobile application development. In Objective-C, you could insert JavaScript into the JavaScript core, and they went to efforts to lock the objects so that you couldn't do more than one thing. But if you used a function, if you called a function, it would get around those locks. And so you could actually run into race conditions in your JavaScript in a way that someone who's used to writing JavaScript would not expect. So there are some exceptions in browser land.
Yeah. Well, and even Chrome does some nifty things in the background to optimize so that, because it was once that browsers actually ran all of their tabs in a single thread. So whichever tab you were on, or even if you had multiple windows, if JavaScript was running in one site, JavaScript couldn't run on another site. And Chrome, I don't know if it's Firefox or Chrome, but one of them was the first browser to allow you to have, essentially each tab was its own thread. Okay.
That was Chrome. That was a big deal for me.
So if I want to get around this problem that I've created with this Python 2 server, so what I could do is, this probably won't actually work. I haven't tested it to know for sure. But I could just in several different terminal windows, I could run several instances of this Python 2 server. It would probably need some sort of option to allow binding to the same port. But essentially I could run 1, 2, 3, 4, 5, as many as I wanted to. But I could run many different processes that all did the same thing, that all were doing static web servers. And that would mean that up to 5 connections could happen at a time. But like I just mentioned, if you don't do this on purpose, you run into the e-adder in use error, which no doubt some of you have run into before, where you have your development process open in one terminal on one desktop and you forget about it, and then you try to open it on another desktop, and then it's like port 3000 is already in use. So that it is actually possible to have multiple processes running on the same port. And if you've ever done this on purpose, you could have run into the alternate problem, which is that every time you open up a browser tab with that web address, it gives you one development site. But when you open up another tab, it gives you a different development site. Because of course, if I can run multiple processes on the same port, I could run, one could be a Python process serving one website, another could be a Node process serving a different website, another could be a Ruby process serving yet another website, and then it would be Russian roulette as to which site you get. But in the simple case, you can just run multiple processes for the same application, and you could handle multiple requests to multiple clients this way. In Node, the way to get that behavior and what the Node cluster module uses, I think it says, cluster workers will use the same underlying handle. So you can pass to the listen function exclusive false, which is already the default for the net module, but I don't believe that that is the default for the HTTP module. But you can pass that in, and then you can actually have multiple processes listening on the same port. And every other language has something similar. This is something that goes down to what is called a syscall. So it happens either on the Linux kernel or the Windows kernel or the Mac kernel. It gets passed all the way down to the kernel, which is actually what's handling network sockets. Okay, so that's what a process is. And the next thing we need to talk about is forks. So a fork, whoops. first of all, Node does not fork. Node has a thing called childprocess.fork. That is not a fork. It kind of sort of emulates a fork in a way, but it's not a fork. A fork is actually kind of like what a GitHub fork is. It's your application is running, well, Git repositories don't run, but your application exists in memory. And when you fork, it copies all of the memory space for the application, whatever variables, whatever value they're set to. So if you have like, when the program starts, X is set to 42, but sometime later in the program execution, X is set to 37. If you do a fork, a true fork, whatever memory is at that exact moment, the fork will be the same. And what will get changed is its process ID in the list of processes. So it's essentially just another process, but the parent process gets to set some variables, then fork, and then the fork will contain those variables different from what the parent was. And this is kind of how old school web servers worked. So Apache and PHP is how people used to do web development back in the late 90s, early 2000s. And Apache as a web server would create forks of itself. And then as many forks as there were, it would handle that many requests. So Apache was meant to handle a single request very quickly as a file server, and then be done, and then be ready to handle another single request. And so there might be 50 forks. And so that means it could handle a maximum of 50 concurrent connections. And each PHP process ran, whoops, I hit the wrong button, ran in that Apache process. And then you had things like Fusion Passenger for Ruby on Rails, which was basically the same thing, except that it was Nginx and it didn't take advantage of Nginx's native optimizations for Ruby, because Ruby didn't support them. But Nginx was basically just a more advanced web server because it actually uses an event loop, which we'll get into that a little bit later. But so if you're ever familiar with mod PHP for Apache or Fusion Passenger for Ruby on Rails, these are both following this forking model or this process model. So we have something, if we needed to handle 1 million requests, we could just have 1 million processes or 1 million forks. So why is this good enough? Why not? It's not good enough because of what I pointed to earlier. These are memory hogs. So for every single process or fork, you have that 40 megabytes of RAM or 5 megabytes of RAM or however many megabytes of RAM that process is just to execute, period, is being taken up, plus the libraries it's loading, plus the things that it's caching in memory, like perhaps some static assets from the file system, et cetera, et cetera. So you balloon memory very quickly and it's not scalable. Also, IPC or inter-process communication is a nightmare between processes and forks. So inter-process communication, meaning basically you have to use a database. I mean, there are some other tricks you can use to communicate between processes, but in the end, we pretty much end up using a database to be able to communicate between processes. And we do this even in the more efficient models, but essentially you have no way, if variable X changes over in one process, you have to define some sort of method to say that variable X changed to communicate that to other processes. And that's just cumbersome, and it's very cumbersome for small apps where the user load is small. So there's, well,